morning, everybody. Thank you for the invitation to this conference. It's a great honor for me to talk about the Euclid mission on behalf of the full Euclid consortium. I'm Veropalumbo. I work as a researcher at INAF, National Institute for Astrophysics in Brera, and I'm a Euclid member since 10 years now. What's not going on? Okay. So we all know about cosmology, the status of the cosmological model. We just heard from the previous talk all the things that we should know. Let me say that there is an urgency to understand, since we know what is we have this beautiful model that explains with few parameters a lot of different observations. Many questions are left open, and the most important one are the composition of the universe. Basically, there is basically unknown. We can only prove it. Volume. The volume. The microphone? Better? Okay. Oh, okay. Mm-hmm. Okay. Just a second. Okay. Okay. So yes, just I was saying, we have to understand what is the origin of the dark universe, basically dark matter and dark energy that makes the most of the composition of the universe today. So this is the goal of future experiments. And Euclid is, of course, one of the most important, that will produce data for the next years. In particular, the dark energy is the component of the universe that dominate the energy budget today, and that is responsible for accelerated expansion. And we know since 20 years, first with the data from supernovae, and then this probe is being confirmed. This has been confirmed by other experiments in the next 20 years. At the moment, all the things point towards the cosmological constant model for dark energy, but future experiments will improve our knowledge of the parameters of the equation of state of dark energy, for example, to see if modification of something different should be understood, and so clarify the nature of this dark energy. And to probe properly dark energy, we need to probe the universe in the range where dark energy has most influence, so in the local universe. And the most important tool to do this kind of study is for sure cosmological surveys that aim at producing maps of the large-scale structure to extract information from the underground from the matter density field. The important thing about cosmological survey with respect to early time epochs like CMB is that we can probe also different epochs by looking at different redshifts, so that we can probe different stage of the evolution of the universe. So this is really important, and of course, around cosmological survey, there has been a lot of work in the last years, and many surveys have been produced. And the future is very bright in this sense, because in the next generation experiment, the so-called stage 4 surveys, are about to be produced, to start producing their data and their results. And this stage 4 survey, which Euclid is of course one of the most important, are basically a huge leap in terms of coverage of the area and the number density of objects. So we expect that the statistical error that we can expect from this survey to reduce dramatically on cosmological parameters. This is also a huge challenge, not only technically to design this survey, to be efficient and fast to sample with this high number density, these large volumes, but also we have to be sure and put particular attention on all possible systematics effect. So what is Euclid in really few words? Euclid is a mission by the European Space Agency with extra contribution with national agency of the member states. and that has the responsibility of the satellite, while the development of the instrument and data analysis and the final scientific results is on behalf of the Euclid consortium. The primary goal of Euclid is to map a huge portion of the volume with an unprecedentedly large sampling with an unprecedentedly large 3D map. And this data set that will be collected during the year of the mission serves different goals. The primary goal of Euclid is, of course, cosmology. And this is a cosmological survey that has been specifically designed to take advantage of the two probes that we just heard from previous talk. So weak lensing and galaxy clustering. We heard that these two experiments are usually complementary. Euclid will do, in its survey, will exploit both of them. But Euclid will also produce a lot of data that can serve different purposes. The cosmological purposes, like, for example, additional probes like galaxy cluster with number counts, or cosmic void, CMB cross correlation, strong lensing. But there will be also a huge amount of data that will be used for legacy science, in particular galaxy age and evolution. So I think many of you can be interested in. Let me also highlight one thing that I like. Euclid is not only a scientific mission, it's also a huge collaboration of people working together, everyone in its own field and together for the final goal. As I said before, there is the mission is operated by the space agency, but the instrumentation and the data analysis is led by the Euclid Consortium, which is an organization of people. We board 2,000 scientists all around Europe, US, Canada, and Japan. So we are all excited to be part of this collaboration. So let's speak about the core science. As I said before, Euclid is focused on cosmology and in producing fundamentally two surveys for the two different probes, weak lensing and galaxy clustering. For the weak lensing survey, we basically are had everything before, but let me stress here what are the most important difficulties for Euclid here. The goal here is to collect to detect a signal that is very, very small, or the order of 10 to -3 in ellipticity, ellipticity, and the signal cannot be observed on one single galaxy. So you have to stack signal for many, many galaxies all together on a huge volume. You need to correlate the signal from millions of galaxies. So you start from the original image that gets that get distorted by the lensing signal, but then there is all the telescope convolution that you have to take into account when you do your data analysis. And all these kind of systematics require an accurate calibration of the instrument, but also an accurate design to ensure that you have a very sharp PSF that will be able to describe the structure of your images. The signal then, after you collect you extract the shear signal, you fundamentally you track down the dark matter density field from the sources up to you, thanks to this tomographic approach, and then you compress this signal in summary statistic like angular power spectrum or correlation function. Out of that, you compare this with your cosmological model, you're basically done. Of course, it's not that easy. And to do that, you also have to have a huge control on your systematics. For example, I'm just listing two of them, but there are many. You have intrinsic alignment. That is due to the fact that galaxies locally can have during the formation correlation of shapes, and this signal is strongly degenerate with the cosmological signal you want to actually observe. And also you have dependence of PSF that depends on the color. So depending on which target you choose, the results may vary. You have to take into account that. The second probe that Euclid will exploit is galaxy clustering. Galaxy clustering is essentially producing a map of the large-scale structure that encodes information from the matter density field that you don't observe directly, but you observe through some tracers. In the case of Euclid, will be start forming galaxies in the redshift between above 1. Then after you compile this map, of which you can see an example here as produced by developers collaboration, you extract statistically the signal inside this map by computing the endpoint correlation function and power spectrum. Of course, the most precise you are in producing your map, the most clean will be your data set. So the goal for galaxy clustering is to exactly pinpoint your galaxies in the 3D volume, and to do so, you need spectroscopic information. Euclid indeed is not only a photometric observatory, it also has a spectrometer on it exactly to serve this goal. And the probe that Euclid will use are, of course, baryon acoustic oscillations, because the volume will be so huge that the signal of the peak will be seen very clearly. We heard everything about baryon acoustic oscillation. Let me add just one point. In this plot, you see a compilation of different measure of distances from different surveys, and the orange region is the one that Euclid will probe, that at the moment lacks lack of data, and is also where future survey, stage 4 survey, will focus on. So we will have information about this region here, and the same holds for the redshift space distortion that measures the effects or the peculiar velocity on galaxy clustering statistics, and can give us information on the linear growth rate, which are also essential to test dark energy model and gravity. And again, due to the fact that the survey essentially now the stage 3 survey are essentially located in the local universe, at the moment there is lack of points in this region here that Euclid will probe. So these are this is the scientific background behind Euclid. Now, let me briefly talk about the design of the instrumentation and the survey before moving on to the update to the mission. The Euclid satellite is designed to observe the sky in the visual and near-infrared bands, and to do it very efficiently, because the goal is to sample 1/3 of the sky over in 6 years. To do so, you have to produce millions of fields with both photometric and spectroscopic information. For this reason, it is mounted. The satellite is a telescope with a 1.2 meter diameter mirror that, in one single exposure, exposed its 2 instruments. The VIS instrument, which is scattered, which is not a single object, but is a collection of objects on the focal plane, gets as the instrument that has been designed for the weak lensing survey. It observes in one single band in the visual band, and is designed to collect data with extraordinary sharp PSF, exactly to fulfill the weak lensing goals. You can see the VIS instrument here, the focal plane. Here is the CCD, is the collection of CCD of the 36 CCDs that forms its focal plane. The second instrument is works in the near infrared. Is a photometer and spectrometer, and it's called NISP. And this is the responsibility to collect the spectroscopic information and for the determination of redshift. And this will be used for the galaxy clustering survey. As I was saying before, the instrument and the observation are organized in such a way to be extremely efficient, and the two will be done at the same time with one single exposure. These are some data about the field of view. You can see the field of view of VIS and NISP. The two are exactly the same, 0.6 degrees squared, compared with something familiar. Let's say we have the full moon that is larger, so the field of view is larger than the full moon, and compared with other survey for space in the near infrared and visual band. So one single exposure is as large as the most deep survey that we have from space now. That's the reason, and we have to collect millions of this field to form to have the full survey produced. And then we have the photometric band. We have the visual band of the photometric band for the VIS instrument, the 3 bands for the near infrared, and the 2 GRISM, so the extension of the spectroscopy range for the 2 GRISM, the red one, this one, and the blue one. and the two that will be used for the service. Some more information about spectroscopy. The spectrometer performs slitless spectroscopy, so there is no targeting and no fiber collision problems. Of course, there are many other problems because when you do slitless spectroscopy, you basically interpose a grism between the beam and the light and your detector, and you get this beautiful spectra on the focal plane. This is a simulation. Of course, these spectra are only along one direction, and you need to disentangle the different sources to be able to extract the redshift for the sources of your interest. To do so, you orientate your instrument, you change the orientation of your grism to allow and take the images of the same field in different orientation to allow the contamination. The survey will be done in with the two different grisms. The wide survey, that is one for cosmological analysis, will only use the red grism, which extension in redshift allows to detect the H-alpha line from star-forming galaxies in the redshift range between 0.9 and 1.8. That is the range of interest of Euclid. There is the possibility that when only one single line is detected, that you have misidentification from other lines, the so-called interlopers, and you want to you have to address this when you do your analysis, and the target spectroscopic error is below 2%. So this is the instrumentation, and then now let's go to the final survey that Euclid will produce at the end of its mission. You can find all the details in the published paper by the collaboration, but what Euclid will produce at the end of its 6-year mission will be two surveys, basically. A wide survey, that is the one that is used for cosmological analysis, that will observe 1/3 of the sky, which you can have a vision here when you have the celestial sphere projected. You see encircled in blue the so-called region of interest of Euclid, where the telescope will point and collect this information. Of course, the region of the ecliptic and of the disk of the galaxy are excluded, as well as other extended sources on the sky. The mission will take this data in 6 years. That is extremely fast, and at the end of its analysis will produce a survey of 1.5 billion photometric galaxies for the weak lensing purposes, marking a huge advancement in terms of quality of the data, and more than 30 million spectra in the redshift range above 1, thanks to the observation of the H-alpha emission light. And in the second plot, you can see how the mission will take this data. You see different fields and different colors refers to the year of the mission. So at the end, the sample region will be the one that you can see with different colors inside the region of interest. Together with the wide survey that as mainly will fulfill the cosmological goal of Euclid, there is another survey that is a deep survey that, as it says the name, is deeper in terms of limiting magnitudes. This survey is split in three different fields, one in the northern hemisphere and two in the southern. And the peculiarity is that while for the wide survey we only use the red grism, for this survey we will use both grism, extending the redshift range of the spectra. And then in this way, we will be able to assess purity and completeness of the spectroscopic survey that will be used for cosmology, as well as understand the probability of a source to be detected as an interloper or not, and to be able to include that in the final cosmological analysis that we'll have to take that into account. This deep survey is also very important for legacy science, because it will be full of information that will be used for galaxy formation, or in a field with low stellar contamination, so are perfect for this kind of study, and all other kinds of calibration. So with the scientific goals, with the scientific tools and all the numbers that I just shown below with respect to the number of objects that we detected and the survey sampled, these are the forecasts that the Euclid mission produced for the at the end for its end of the mission. In particular, here is shown the figure of merit on the parameter of the equation of state W0 WA. There are two settings, pessimistic and optimistic as well, because we're doing forecast here. So we don't know what is the true, what will be the truth, but it will be something in between. The pessimistic setting means that we are assuming numbers that are lower number densities, lower completeness, and so on and so forth. And the optimistic setting, which we said we are in best possible situation. The lesson learned from this forecast analysis, first of all, is that the best results Euclid will obtain will be obtained when you put probes together. So, of course, it's important to study the probe one by one and to understand all the systematics, but the most important results you will get when you put probes together, not only the core science probes, so galaxy clustering and cleansing, but also any other source of information, so the photometric galaxy clustering and cross-correlation with CMB. When you do that, you reach the goal of Euclid that is right in its first mission goals. That is this figure of merit of 400 on parameters of the equation of state, even in the pessimistic sample, and we hope to be even better than that. On the plot on the right, you see instead the error bars that you expect in both pessimistic and optimistic, in the optimistic scenario, when on cosmological parameters of the extended W0 extended dark energy models. And you see that you have your improvements when you put probes together. For example, you see a huge jump in the error bars when you go from the orange one to the yellow one, and so on. So we expect to see, we really want to see this number as soon as possible when the real data will come out. To conclude my talk, let's just report a bit of the status of the mission. As we all know, the mission has been launched 2 months ago from Cape Canaveral and has completed this path from L2 to L2. Right after the launch of the mission, all the instrument has been turned on and tested for the first time in space conditions. And starting the so-called commissioning phase, in which there is the assessment that everything seems to work correctly. This commissioning also gifted us with some early images that start to demonstrate what are the capabilities of Euclid. And this is, for example, one field of view of this. So in the visual, you can appreciate the quality of this image that is not usable for scientific analysis. It's just really a raw data. But still you can see it's the 36 CCDs, of which you see a zoom here, and you see the quality of the data that we all wanted to see during the preparation phases. You have the same for NISP. So you have here in near infrared, here you have the difference in PSF because you're looking at another wavelength. But what is important for NISP, that is important also for me, that I personally work in galaxy clustering, is that the production of the first spectra when used in Gris mode. Each one of this line is a spectra of an image, and you can appreciate some emission lines. That is what we want to see at the end. What are actually now? Actually, we are now completing we are now in the transition between commissioning and performance verification. We are now facing problems that are common to a mission at the beginning. In particular, we have a software problem with fine guidance sensor that should be that is not really able to fix the pointing at the moment due to contamination of the field. And that will be solved hopefully very soon with the help of industry. And when this will be completed and a stable solution will be found, the operation of performance verification will continue and will last for 3 months. And at the end of this period, the survey will officially start and will last for 6 years, in which the Euclid will observe the sky without stop. for the audience that is not really involved in Euclid, the important dates to remember are the dates on which this data release will be hopefully made public. This will happen in 2 years. From the beginning of the survey, that at the moment is scheduled for the beginning of next year, so mid-2025 for the first sixth of the survey to be released, the data release 1, and then in the next years there will be data release 2 when half of the survey will be completed, and at the end the full survey and data release will be released. At each data release, there will be tons of work describing the data, describing all the results and all the stuff that we do in the consortium, and we hope to do all together beautiful, fantastic science for the future. So this is really just the beginning. Let's hope for the best and stay tuned for more.